Eisenstein from Harvard University. He's presently the director of Sloan III, and he's here for the entire week. So if anyone wants to meet with him, just let me know. He did his PhD in Harvard University as well, and then did a postdoc at the Institute for Advanced Studies in Princeton. Then was a Hubble Fellow at the University of Chicago, and then moved to Arizona, to the University of Arizona in Tucson, where he was a faculty member for how many years? Almost 10 years. And now, I think about a year ago, he went back to Harvard. So today he's going to talk us about the cosmology, dark energy, and cosmic sounds. Please, Daniel.
Well, it's a great pleasure to be here this week. It's been really wonderful to meet lots of new people and to see the Institute. I'm going to be telling you today about work in cosmology on the baryon acoustic oscillation. And just to note, a lot of my collaborators here, but really there's many, many people who have been part of SDSS that have helped to collect this data set. So the general topic here is dark energy. And as probably most of you know, in 1998, two groups argued from supernova data that the high redshift supernova appeared more distant than they were expected to be, and that this indicates that the expansion rate of the universe is accelerating. This is a completely remarkable thing. It's as if we threw a ball up in the air, and instead of coming back down and hitting us on the head, it continued to accelerate out into outer space and into the infinite distance. And so many possible explanations have been advanced for what might cause this. There's the famous example from Einstein of the cosmological constant, but there's also ideas of new low mass, new forces in the universe that might be mediated by low mass fields. There's ideas that a familiar force, gravity, might be altered in some way on very large scales. There's ideas from string theory about extra dimensions and how this might change gravity. And really, the number of feet of journal that have been used to try to explain dark energy is quite large at this point. And the reason that this is so is that all of these ideas are exotic in some form or another, and it's not, there's no one idea that is so aesthetically compelling that it just jumps forward to the front of the list and says, we should pick this one just because it's pretty. And so we are left observationally trying to select between these various concepts, and one of the main ways that we can try to learn more observationally is by improving the cosmological distance scale to 1% and better. And so what I'm going to be describing today is a method for measuring cosmological distance and thereby learning about dark energy. So the outline of the talk, I'm going to spend a fair bit of time describing this idea called the baryon acoustic oscillations and why they can be used to define a standard ruler in cosmology, an object of known length. I'll go through the pedagogy and linear theory in a fair bit of detail, and then describe what we've learned in nonlinear theory. And then I'll move on to the observational side of things and tell you about our detections of this in the Sloan Digital Sky Survey luminous red galaxy sample and what we've learned about cosmology from that. And then I will give a taste towards the future with upcoming surveys, and in particular I'm going to focus on SDSS-III, which of course this institute is a member of and that I work a lot on. So I wasn't sure if there'd be any students in the audience that might not be doing cosmology very much, so I thought I'd just include this slide. So just to remind you of some of the cosmological jargon, the size of the universe expands, and we parameterize this with the scale factor A of t, and of course the inverse of that A of t is the cosmological redshift, z. And what this means is that redshift, scale factor, and time all get used interchangeably by cosmologists as a time axis because there's a monotonic relation between all of these. The Hubble constant is the proportionality between velocity and distance for local objects, and the Hubble parameter as a function of time is simply a logarithmic derivative of the logarithm of the scale factor. So once you've specified the scale factor, you've specified the Hubble parameter, and vice versa. We write the present-day value of the Hubble parameter as h naught, which is 100 times a little dimensionless constant h, kilometers per second per megaparsec. So you'll see in my talk various points where little h's will appear in slides, and that's just to remind you of the present-day value of the Hubble constant. Now, with any expansion, just like if you were to shoot a rocket ship up into space, there's a critical velocity at which point things will escape to infinity, but only reach infinity at asymptotically zero velocity. And it's the same way with the universe. Once you specify the amount of expansion, there's a critical density at which point that expansion would exactly balance off the density of the gravity from that density, and that's called the critical density. And so that critical density scales as the Hubble parameter squared. We typically measure densities by the ratio of that density to the critical, the density in question to the critical density. So for example, omega matter is the matter density divided by the critical density, but you can do that for other quantities. The reason I mention this is that one should then remember that omega matter is not the density of the universe. It is the density divided by the critical density. And in particular, if you want to measure the actual proper density in grams per cubic centimeter, it's proportional to omega matter h squared or omega baryon h squared. There's always h squareds that come in. So in my talk, you will occasionally, I will at several points talk about omega matter h squared. And I just wanted to remind you that the reason we're doing this is that's actually the proper matter density. Okay, so now on to acoustic oscillations. So you're probably familiar with this idea from the microwave background. So on the right here is the picture of the hot and cold spots in the microwave background, positioned on the sky. And you can see here there's fluctuations on all scales. There's fluctuations on large scales. There's temperature fluctuations on small scales. But if you take a picture of that map and you just blow it up to a smaller region, there is actually a characteristic size of the blobs that your eye can pick out. You can see in here there is just a characteristic scale of these blobs. And these are caused by this acoustic oscillations. If we take this map and we basically decompose it into multiple moments, or equivalently take a Fourier transform of it, and plot up the average Fourier coefficient as a function of multiple moments, we get what's called a power spectrum. And this power spectrum shows a dramatic rise at 1 degree scale, which is this characteristic size of the blobs in the universe, and then a harmonic series of peaks after that. And those are the acoustic oscillations. So if you don't like this data, this is data from the WMAP team where you can start to see the first few oscillations. But there's been beautiful work recently released from the South Pole Telescope team where you can now see, acoustic oscillation 1, 2, 3, 4, 5, 6, 7, 8, and maybe you believe the 9th peak. So the data's just gotten phenomenally good as to how many peaks you can really see in the early universe. And with the Planck satellite coming out, next year, the error bars out at the far right of this plot will be about the thickness of the line. So data's going to get very, very good quickly. Okay, so what is actually causing this? Well, these oscillations are actually caused by sound waves that propagate in the early universe. And the key epoch in the early universe is the epoch of recombination, redshift of 1,000, about 400,000 years after the Big Bang. And the reason that this is important is that the early universe is hotter and denser, and once you get before redshift of 1,000, the universe is sufficiently hot and dense that the hydrogen in the universe is ionized. And in that ionized plasma, the microwave background photons that try to travel through that plasma get scattered by Thomson scattering. So their mean free path becomes much shorter, or their mean free time becomes much shorter than the age of the universe at that time. So this is important because if you take a packet of this plasma and you squeeze it, the photons can't escape, and they're basically caught in a collapsing box, and that means that they get upscattered, they get blue shifted, and when they get blue shifted, they end up providing more radiation pressure. So you take a packet of this plasma and you're squeezing it, and the radiation pressure is increasing. And eventually you'll reach a point where the radiation pressure will actually be stronger than the compressing force of gravity, and it will push back. The region will expand back outwards. It will actually overshoot, become too cold, and hence underpressured, and the rest of the universe will push back on it, and the whole thing will sit there and oscillate. So this is exactly like a sound wave. It's just like the sound waves traveling in this room, but the restoring force is not the random motion of the gas particles, but rather it is the radiation pressure of the photons. But aside from that, it really is just a compressional sound wave. After recombination, the universe becomes neutral. Now the photons can travel freely through the gas. That's why we can see the microwave background at all. And now if you take a packet of this gas and you squeeze it, then gravity keeps pulling and pulling and pulling, and you get a gravitational runaway. So you have this basic transition in the early universe from early times when the perturbations are stabilized and oscillate as acoustic waves to after recombination when the perturbations are unstable due to gravitational collapse. So if we now consider what this implies for the clustering of matter, if we consider a universe where we only put an overdensity at a single location, so it's homogeneous everywhere else, but it's just overdense in one location initially, and it's overdense in dark matter, it's overdense in gas, it's overdense in photons. And because it's overdense in photons, it's also overpressured. And the way that an overpressure tries to equilibrate is by driving a spherical sound wave out into the ambient medium. So you have the dark matter in the center, and you have this outgoing wave in the plasma that travels out at the speed of sound until the epoch of recombination. Now, the speed of sound at these times is very high. It's 57% of the speed of light because the radiation pressure of the photons is so large compared to the relatively small inertia of the cosmic gas. And so you travel outwards until recombination. At recombination, the wave stalls, the sound speed drops, and you end up depositing the gas in a spherical shell whose radius today is 150 megaparsecs, about 500 million light years. Now you have an overdensity in the center from the dark matter, an overdensity in the shell from the gas, and both of these regions will now create gravitational instability. They'll attract more gas and dark matter to them and preferentially form galaxies both in the center and on this shell. So you have this prediction that pairs of galaxies will be preferentially separated by 150 megaparsecs, the radius of this shell. So that's the prediction from these ideas, is that galaxies should be slightly more likely to be separated by 150 megaparsecs than by 120 or 180 megaparsecs. That's the signature we're going to look for. Now, in the data, you don't get to go and look for little bullseye patterns because really the universe has been perturbed everywhere. Every location in the universe has thrown off a spherical sound wave, and they've all created these imprints, 150 megaparsecs from them. So you don't get to look for single, bullseye patterns in the data. Instead, you have to use signal processing techniques like the correlation function or the power spectrum to try to extract this characteristic clustering scale. So I'm going to now say the whole story again, but animate this with calculations from an early universe Boltzmann code. This is code CMB-fast. And what you're going to see here is the perturbation starting off at the center and then expanding. Here's radius in megaparsecs in a coordinate system that's expanding with the universe. We're going to start at some very early time, 100 years. And there's 4 curves here for dark matter, gas, photons, and neutrinos. And please remember that all these perturbations are tiny. This is all linear perturbation theory. We're talking about very, very small perturbations. So I'll start this going. And you see that the dark matter is staying at the center. The gas and photons are locked together, traveling outwards in this outgoing pulse. And the neutrinos are leaving the center. They don't interact with things, so they get to smooth themselves out and move around. Okay, we've now reached the epoch of recombination. The photons are beginning to separate from the gas. And as time moves forward, the photons and the neutrinos will spread themselves thin because they're in an optically thin medium, and the gas and the dark matter will stay more or less in place. So there's the wave starting to come to a halt. Now we have the dark matter in the center, the gas at the far at 150 megaparsecs, and now the dark matter will attract some gas, the gas will attract some dark matter from the bulk, and the two will come back into agreement as we head towards redshift 0. So now we will preferentially form galaxies in the center, galaxies at 150 megaparsecs radius, and that's the characteristic scale we're looking for in acoustic oscillations. Okay, so in the first slide I showed you from WMAP, we saw a series of oscillations. And indeed, when you look at things in the power spectrum, you see series of oscillations. In the correlation function, you only see a single peak. Why is that? Well, it's actually rather easy to understand. When you talk about a power spectrum, you're talking about the response to a plane wave. And if we think about one crest of the plane wave, it's overpressured. It's going to drive a planar sound wave out into the ambient medium. That planar sound wave will travel out for 150 megaparsecs. And if at recombination it finds itself on top of a subsequent crest, another crest in the plane wave, then you'll get constructive interference and you'll get a peak in the power spectrum. If it ends up in the trough of a plane wave, you'll get destructive interference and you'll get a dip in the power spectrum. So the single physical scale of 150 megaparsecs gives rise to a single peak in the correlation function, but it gives rise to a harmonic series of constructive and destructive interferences as you change the wavelength of the perturbation in the power spectrum. Okay, so why do we care about this? Well, the reason we care from the point of view of dark energy is that this distance of 150 megaparsecs is actually something that's very easy to calculate. It's simply the distance that the sound waves could travel. Well, how far does sound travel? This is a beginning freshman problem, a beginning physics problem. It's the speed of sound times the amount of time you have to travel, right? That's we'd all agree on that. In detail, the speed of sound depends upon the ratio of pressure to density in the fluid. That depends upon the baryon to photon ratio, which we usually write as omega BH squared. And in detail, the amount of time you have to propagate depends upon how much time the universe spends in the matter-dominated phase compared to the radiation-dominated phase. That depends upon the matter-to-radiation ratio, which we usually write as omega matter H squared. But given those two quantities, omega matter H squared and omega BH squared, you can compute this distance that the sound could travel exactly. Now, wonderfully, the microwave background anisotropies, the relative heights of the peaks and troughs in that WMAP power spectrum, allows us to measure exactly these two quantities, the matter-to-radiation ratio and the baryon-to-photon ratio. So from microwave background data, in particular the latest data from WMAP, you can predict this sound scale to about 1%. And with the upcoming Planck data, this number will go down to about 0.25%. So effectively, the early universe, our measurements of the early universe, allow us to predict an object of known size, a particular scale in the universe, to about to sub% accuracy. And if we now go into a redshift survey, we can try to use this meter stick to measure distances. And in particular, in cosmology, we can do this two different ways. If I set up the meter stick along the line of sight, then this will correspond to a difference in redshifts that we measure. And that difference in redshifts is related to the scale by the Hubble parameter at that redshift. Alternatively, if I turn the meter stick into the transverse direction, then it corresponds to a given angle, and the ratio between the scale and the angle that we measure is something called the angular diameter distance. So with this method, you can measure the angular diameter distance and the Hubble parameter as a function of redshift, and thereby test your cosmological model. Okay, so this sounds straightforward to do. All we need to do is go out and map the universe in 3 dimensions, map the matter in the universe in 3 dimensions. The problem, of course, is that we do not get to see the dark matter very well, and in particular, it's very hard to make maps of dark matter in 3 dimensions. So we have to have some kind of tracer by which we can infer the cosmic structure. And a very popular one to use is galaxy redshift survey. So we're using the large-scale distribution of galaxies in order to make a 3-dimensional map of the universe. And you then worry that there's complications, that everything I've described up till now is about linear perturbation theory, which is appropriate in the early universe when the perturbations are very small. But today, galaxies are clearly a phenomenon of the nonlinear structure collapse of the universe. So you could worry that galaxies would, that the nonlinear structure formation would have obscured the acoustic oscillation signature. You also worry that the galaxies are themselves a biased tracer of the mass. They're not necessarily a completely representative tracer of the underlying density field, and so you could imagine inconsistencies due to that. And finally, when we measure a redshift to something, it's almost proportional to distance, but there are small deviations known as peculiar velocities, and we have to worry that the redshifts that we measure are not, in fact, giving us an accurate 3-dimensional distance map of the universe. So indeed, all 3 of these effects partially degrade the acoustic oscillation signature, and I'll describe that in a minute, but it turns out that the systematics are very small, and it basically boils down to the idea that this length scale of 150 megaparsecs is very much larger than the typical collapse scale of that forms galaxies and even clusters of galaxies in the universe today. So we're on very large scales, and that's what really saves the method. So observationally, when you want to go out and make a map of the universe, this is actually now a pretty well-refined method. We have lots of work over the past 30 years about how to make these maps and how to diagnose and remove systematic effects in the data. And in general, this application is a lot easier than the basic task of measuring the power spectrum, because the acoustic oscillation signature in the power spectrum is oscillatory. And so you basically have an extra differential aspect of the problem where you're able to difference off the behavior on different scales. And this turns out to be very useful for negating systematic errors. The other thing to note is that basically we are still talking about, when we think about measuring a power spectrum like this, in this case, we're trying to measure the horizontal position of these oscillations. And whereas the vertical position has to do with the density and homogeneities in the map, the horizontal axis is actually all about measuring angles and redshifts. It's measuring, big distances and separations in the universe. And astronomers, of course, have lots of trouble measuring certain quantities, like flux is actually rather difficult to measure accurately. But angles and redshifts we do incredibly well. Right? Those are things where getting to 10 to the minus 3 precision is absolutely trivial. So that's another strong aspect of the method. Okay, so let's think about nonlinear structure formation. As I said, everything I said before was about linear structure formation. Well, what's happening nonlinearly? You have a couple points, and they're separated by 150 megaparsecs initially. As structure forms, these points get moved around in the universe because of the large-scale gravitational forces in the universe, and they will end up, perhaps moving around by order 10 megaparsecs. So when they started off at 150 megaparsecs, they ended up at 140 or 160. This is bad because it takes the acoustic peak and tends to spread it out. So here I have, here's a correlation function. This is actually an H inverse megaparsecs, but here's a correlation function initially, and you can see it has a nice strong feature. And as you go to lower and lower redshift, the acoustic peak is getting spread out, and hence moving to lower contrast and broader shape. This is annoying from the point of view of measuring distance, because our goal is to measure the centroid of this peak, and the lower, as you make it lower contrast and broader, you will get worse errors for a given amount of data. So that's bad. But it doesn't actually correspond to a bias in the method. A bias would correspond to actually systematically moving 150 megaparsec pairs inwards or outwards. You need to systematically take things at 150 megaparsecs and move them inwards towards 149. And that is not obviously hard to do. For example, if I have two overdensities, you would expect them to fall towards each other. So you'd say, okay, well, things might typically move inwards. But the correlation function is actually a square quantity, right? So it's the product of two densities. And that means if you have two underdensities, they also count positively towards the correlation function, but two underdensities will fall away from each other. So you have a first-order cancellation in the relative motions that tends to protect the effect. And so one actually expects that the mean shifts should be less than 1%, and I'll show you here in a minute that the simulations show that it's around 0.25% shift. So here's these slides. So these are slides from in-body simulations where, just to focus on the hollow points for now, but this is the acoustic cell shift as a function of redshift, and you can see that as you get down towards low redshift, you're talking about shifts of order 0.2 to 0.3% due to nonlinear structure formation. When you go to consider galaxies, then if you take the halos in the simulation and paint galaxies on them, then you get additional shifts, which is shown here, where if you go to rather high bias, you can get shifts of order, again, 0.5%, less for lower bias cases. And it turns out that the effects of these are very well matched to a calculation by Padmanabhan and White of second-order perturbation theory. So really, we have both a simulation and an analytic evaluation of these shifts, and they come in good agreement, and they're all below 1%. Now, later on, I'll show you how we actually think we can remove these shifts entirely. So that'll be later in the talk. Okay, so to wrap up this portion, the virtues of the acoustic peak is created by physics at redshift of 1,000, where the perturbations are apart in 10 to the 4, and that means that linear perturbation theory is an excellent approximation. It's producing a large feature in the universe that you can actually measure geometrically in the universe, large angles, large changes in redshift. And it's a manifestation of a preferred scale, and it's a very large scale where the dominant effect for moving it around is gravity, and the gravity is actually something that we routinely simulate. So we actually don't, there's no particular reason to be concerned about nonlinear effects in gravity. We can simulate them quite nicely. We have no way at this point no known way of how to create a sharp scale at 150 megaparsecs with low redshift astrophysics. So that's a plus. We can measure absolute distance, so it's measurement of distance, but it's also measuring absolute distance, and not only at low redshift, but actually going out to redshift of 1,000 with the microwave background. And the method has a cross-check because you can measure the Hubble parameter and you can measure the angular diameter distance, but one of these, the angular diameter distance is supposed to be an integral of the Hubble parameter, and if you got the wrong answer, then you would think that something was up. Okay, so that's been an argument for why this method is robust, but now we should worry about whether it is in fact sufficiently precise to be interesting, and just focus on the red points here. This is the error bars that you could get for a slice in redshift of 0.1 from a aggressive survey, 30,000 square degrees, lots of galaxies. But you can see that you can achieve precisions of order 0.3% in distance for every 0.1 in redshift. So that's, in fact, very compelling precision that's available for the cosmological distance scale. For the Hubble parameter itself, this is a little worse. It's more like 0.6%, but still at high redshift to measure the Hubble parameter to 0.6% would be a wonderful thing. Okay, so now let's move on to some observations. So we've been doing this work with the Sloan Digital Sky Survey, which is the world's largest galaxy redshift survey. We took digital pictures of a quarter of the sky in 5 different band passes, yielded about 350 million objects, and then spectroscopy of about 1.5 million additional objects, mostly galaxies. The project began in 1990, started taking data in 1998, and the SDSS-II phase finished in 2008. I'll tell you about SDSS-III towards the end of the talk. So here's an entirely not random picture of the universe's Tacoma cluster. And the reason I show this picture is that these big, bright galaxies in the centers of clusters are very luminous galaxies. They're very easy to select, and these are the types of galaxies that we use to make the maps of the largest regions of the universe, the luminous red galaxy sample. So here's a picture of that where we're now, this is a pie diagram, so you're starting at the Earth, you're looking at redshift, and this is a swath of the sky about 90 degrees long. And every dot here is a galaxy, one of these luminous red galaxies, going from redshift 0.16 to 0.47. And I put this bullseye pattern here just to remind you of the scale of the acoustic oscillation. So this acoustic oscillation signature of 150 megaparsecs is still a large scale in the universe. It's about 6 degrees on the sky, but still smaller than the size of the survey. Again, you shouldn't see bullseye patterns in this data, but it's that's the size of the acoustic oscillations. So this was the data we published in 2005. This was the correlation function of these luminous red galaxies, and this bump out here at 100 h-inverse megaparsecs is the acoustic signature. The 3 lines here are different theories with different values of the matter density, and the magenta line is the best fit model without baryons, pure cold dark matter, and that was rejected about delta chi squared of 11.7, so slightly over 3 sigma. You could then use this data to try to measure cosmological distance. So maybe if I go back here, how would we measure cosmological distance? Well, if we had used the wrong distance in our, let's say we used when we were turning redshifts into distance, we measured a whole bunch of galaxy redshifts and we're turning them into distance. If we use a cosmological distance scale, which is a factor of 2 too large, then all of our distances would be a factor of 2 further away. All of the separations would be a factor of 2 too large. And so this acoustic peak, instead of being at 100 megaparsecs, would have appeared at 200 megaparsecs, and therefore wouldn't match where the theory is. So it's basically, as you change the distance scale, you're moving the data left and right relative to the theory predictions. So from that, you can measure the distance to redshift of 0.35, which is the median redshift of the sample, and we got a distance estimate here of about 1,400 megaparsecs. So that turned out to give us an error bar of about 4% on the cosmic distance scale. So we measured the ratio of the distance to 0.35 compared to the distance to redshift of 1,000 to 4%. And when you then take the omega matter h squared that we get from our data or the omega matter h squared that we get from the WMAP data, they agree with good precision. So we have both methods give estimates of the matter density and come out to about 10% precision. And when you use that, then you actually are setting up what that scale really is. And that allows you to measure omega matter to be about 0.27 plus or minus 2.5%. Since then, we've continued to study this in larger data sets. So here's the latest data release from SDSS-II, the final data release from SDSS-II. And this was the analysis by Percival et al. Of the acoustic oscillations in the power spectrum. So now you can see all these oscillatory patterns that give a measurement of the cosmological distance scale from the power spectrum. With that, we tried to fit a distance actually at two different redshifts, redshift 0.2 and also redshift 0.35. And this is the constraint that we got from, where are we? This is the constraint from redshift 0.2 and 0.35, giving these distance constraints. I like to express this result not in terms of the two distances, but rather as the sum and the ratio of the two distances, so the average and the ratio. So the average gives you a distance about to redshift 0.275, and that turned out to be a 2.7% measurement of the distance. So we're slightly below 3% measurement of the distance. The ratio between 0.35 and 0.2, we got a number, and it's consistent with lambda CDM and about 3 sigma different from omega matter equals 1. It's not a very stringent constraint, and that's simply because the baseline between redshift 0.2 and redshift 0.35 is not really large enough. There's not enough lever arm to get a nice constraint out of that. But there was excellent agreement between the data sets from BAO and also from microwave background and supernova data. So here's a plot of omega curvature. So the spatial curvature of the universe versus the equation of state of dark energy, assumed constant here. And here's the constraint that you get from WMAP plus BAO signal. Here's the constraint you get from WMAP plus the supernova data. Sorry. And you can see they give excellent agreement, and they overlap right back at a spatially flat universe with a cosmological constant. So this is a non-trivial statement. We actually opened up 2 degrees of freedom in the cosmological model, and yet the data pushes us back towards the concordance model of flat universe with cosmological constant. The precision is pretty impressive. So here's the precision of omega curvature, which is a 0.8% measurement of omega curvature. So the universe is very, very close to flat, to within 1%. I'll come back to other numbers here later on. Since then, there have been new BAO detections published. So the Wigglesy survey on the AAT measured 200,000 galaxies over 800 square degrees up at higher redshift, and they published a acoustic oscillation detection that gave them about a 4% measurement to redshift 0.6. And the same overlapped group used the 6DF galaxy survey now to measure galaxies at very low redshift, and they found also an acoustic oscillation even at very low redshift and got about a 4.5% measurement at redshift of 0.1. So we now have a Hubble diagram from BAO with the 6DF point, the 2 points from SDSS, and the Wigglesy points group ended up dividing their sample into 3 bins. So we now actually have measurements of cosmological distance going out as a function of redshift. Again, the agreement here with the supernova data has been really encouraging, and the data set keeps coming back to W's around cosmological constant and flat universes. Okay, so now I'm going to tell you about the work that we've just recently completed and put on AstroPH, I think a couple weeks ago, where we're using the same data set as the SDSS-DR7, but we're going to use a different analysis technique to try to improve the precision on the acoustic oscillations. And this goes back to the idea I told you about at the beginning of what happens from the nonlinear collapse. So if you take these two points that are 150 megaparsecs apart, and they're getting moved around by the bulk flows, these flows are largely created by the large density perturbations of the universe, creating large-scale gravitational flows. Well, those density perturbations are exactly what we just got done measuring in our surveys. So we can take the density perturbations that we measure, predict what the flow directions should be, and move the galaxies back along the flow directions to try to restore things back from the 140 or 160 megaparsecs back towards the 150 megaparsecs. And so when you do this, you can actually undo a lot of the nonlinearity on large scales and restore the precision that would have been available in the linear regime. And these are plots just showing this in simulations where the black is the input model, the blue is what you get out. The blue is what you get out of the simulation in full nonlinear, and the red or magenta is what you get if you just do this simple exercise of trying to move things back. And you can see that you go a long way towards restoring the linear regime. So this is a plot. This is a movie trying to show this in pictures. Let me start the movie over here. So we're going to start from a homogeneous universe where we've painted the center point and then some points on a ring, and we've just let them distort by the nonlinear flows, and you can see that they end up separated from the ring, which is where the linear regime would be. Now, if you just try to move things back by the large-scale flows, you tend to push things back towards this ring, and that improves the contrast on the acoustic peak. So that's the idea of reconstruction that we're trying to employ. We've tried this in simulations and found that in addition to, yes, we find that the error bars get smaller, but in addition, we also find that it removes the shift of the acoustic scale. So early on, I told you that we do find that there's a characteristic sense in which the pairs tend to fall towards each other by about 0.25%. But when you turn on this reconstruction, it actually moves things back towards the original zero line with now a precision of 0.02%. So when you do reconstruction and simulations, you actually get back the linear regime value of the acoustic scale to 0.02%. When you turn on galaxy bias, again, you move things from what was originally of order 0.5% shift, again, back towards being consistent with zero, now with about 0.1% uncertainty because the simulations weren't quite as large a volume. We're obviously working on more simulations. So this is a really good thing. And why does it come about? Well, it's basically the galaxy bias effect was coming about because you have these inflows of overdense regions falling towards each other and underdense regions falling away from each other, and bias is causing you to miss weight. It's causing you to assign different weights to the infalling regions versus the outflowing regions. So you're breaking this cancellation that was happening between the two. But if you, in correcting for the large-scale flows, if you can just remove the flows entirely, it doesn't matter how you weight things anymore. If you can weight zero however you like, and you still get zero. So this has turned out to be a very effective thing because basically, you could think about how you would like to predict this shift and remove it, but in fact, if you can fix it in reconstruction at the beginning, then you don't have to worry about how to make a model of galaxy bias, for example. Okay, so we have a series of 3 papers. Nikhil Padmanabhan, Xiaoying Zhu, and Kushal Mehta were the first authors, and this is presenting a new analysis of the SDSS-II DR7, data release 7, luminous red galaxy sample. This is the first time that we've included reconstruction, and it basically improves the errors as if we had tripled the volume of the survey. Now, tripling the volume of the survey may not sound like that big a deal, but if the survey costs $100 million, getting 3 times of it is actually a big cost savings for just having changed the analysis technique. So this is a plot that Nikhil made for the results of this reconstruction on mock catalog. So this is now fake data, and in fact, it's about 160 examples of the Sloan survey, so the noise is really, really good compared to what we would have in the actual data. But this is now the clustering across the line of sight and along the line of sight. And this is the correlation function times r squared. So this is now the acoustic ring. This is the acoustic scale along the line of sight versus across the line of sight. Now, when this is in real space, when you go to redshift space, then this becomes distorted, and this is because overdense regions that are falling towards each other the peculiar velocities make them seem even closer than they would have been. This is a famous effect originally worked out by Nick Kaiser that creates large-scale distortions in the clustering maps. You can still see the acoustic oscillation ring. In fact, even along line of sight, there's still a ring, but you've created this major squashing. Now, in Reconstruction, because we're estimating how all this material in the universe is flowing around, we can actually correct for the large-scale peculiar velocities as well. And so when we do this with Reconstruction, we get this very nice restoration of the isotropic symmetry of the problem on large scale. So this was a really nice example of Reconstruction working on large scales. On small scales, there's too much complexity. You can't really undo it all. So you can still see signatures of the redshift distortions on small scales. This is the origin. That's zero lag. But on large scales, it looks really nice. So in our correlation function, this is the latest correlation function from SDSS, overplotted with the best fit model. And you should remember here that these error bars are all highly correlated, so you really need to use the full covariance matrix. We do that in the calculation. We get chi-squareds per degree of freedom, 48 on 52 degrees of freedom. So this is a good fit to the data. And this gave us an error bar on the cosmological, on the location of the acoustic peak of 3.5%. So that was the result before Reconstruction. After Reconstruction, you can see that the BAO peak has become more obvious. And now the precision of the measurement goes down to 1.9%. So this idea of going from 3.5 to 1.9% is the thing that's equivalent to tripling the survey volume. So this is really nice. This says we've measured a cosmological distance to 2%. It's the first time that anybody's been able to get to that kind of precision on a cosmological distance scale. Detection significance is actually a subtle issue because you have to decide what your null hypothesis really is. So the significance relative to a model where we've just erased the BAO entirely but given a lot of flexibility to try to fit things is a delta chi-squared of 18. But that's a non-physical model. You don't really have it. We don't have any physical model that would omit the acoustic peak. Instead, you see the acoustic peak at enormous significance in the WMAP data. And the question at low redshift might not be does it exist, but rather where is it? You really are trying to, it is there in the WMAP data. Where is it in the low redshift data? And that gives a much higher significance. That's the red lines here, where you're often up above delta chi-squared of 25 until you try to move the acoustic scale out to enormously larger distance, out towards 200 megaparsecs and beyond, where we're not measuring things. So you have to really push the acoustic scale out to large scales to make it disappear. Okay, so here's our latest Hubble diagram. So here's the 60th point, our new point of SDSS-II here, and the point from Wigglesy here. This is distance versus redshift. The gray line here is the result from the WMAP data if you assume a flat universe with a lambda CDM with a cosmological constant. And this is not a fit to the data. The gray line here is the prediction from WMAP assuming a flat universe with a cosmological constant. And you can see it goes through the data points beautifully. So if I now take the best fit model and divide by that, I get this line on the graph. So here's the ratio of distances versus redshift. The gray band is the range of the 1 sigma range of in the WMAP prediction. So you can see the data is in really nice agreement with the predictions from WMAP at the few percent level. But if you now change the assumption of flatness or cosmological constant, then the predictions from WMAP change. And so in particular, if you look at the blue line here, the blue region is the prediction from WMAP, assuming a cosmological constant, but making the universe have a curvature, be an open universe with a 1% curvature. And you can see that moves the blue line down significantly. Now you would start to have tension with the acoustic oscillation data. Or if you like, you can keep the universe flat and instead have an equation of state for dark energy, which is W of minus 0.7 instead of W of minus 1, and that gives you this line in here in the data. So you can see that these measurements actually have a lot of constraining power on the cosmological model. If you start altering the assumption of spatial curvature or the assumptions about dark energy, you actually can move the prediction quite a lot. So if we use this to measure cosmological parameters, here's a model that's a cosmological constant but with curvature, and we have omega matter and omega curvature. WMAP alone gives you a rather big degeneracy in this space, but with the BAO you get a nice small constraint, and our curvature constraint is around 0.5%. Alternatively, if you want to keep the universe flat and have a constant W, then you get this constraint. W is minus 0.9 with error bars of about 13%. If you combine the two and have curvature and constant W going on, then the result is similar to before, that if you have, BAO data here, you get this constraint. If you have supernova data, you get that constraint. If you put the two together, you get this nice constraint, which is really zeroing in on a flat universe with a cosmological constant here, with about 8% uncertainty in the equation of state and 0.6% uncertainty in the flatness. Now, a very nice aspect of this is that if you combine the WMAP data, the SDSS data, and the supernova data, you get a very stable result, very stable outcome for the Hubble parameter and omega matter, regardless of what dark energy model you pick. So here is the plot of H naught versus omega matter as we make the dark matter model, the dark energy model, more and more complicated, add spatial curvature, whatever you like. And it keeps coming back to the same answer. And it's worth understanding why this is. So it's basically that it's a reverse distance ladder. We're used to the distance ladder where we start measuring objects nearby and then measure relative distances out a little further and then measure distances out a little further, and we eventually get out into the Hubble flow when we claim we've measured a Hubble constant. Here it's the reverse. We've used the WMAP data to measure omega matter H squared and omega BH squared. That's allowed us to set up this measurement to infer the sound scale at redshift of 1,000. We then use the acoustic oscillations in SDSS to measure that same scale at redshift 0.35. That gives us a distance to redshift 0.35. And then we use the supernova data to connect the distance to redshift 0.35 back down to the local universe at redshift of, a few hundredths. And so we've actually really tied the distance scale from redshift of 1,000 all the way back to redshift 0, and that's what's giving us this measurement of the Hubble constant and omega matter. So we find Hubble constants of about 70 plus or minus 2 kilometers per second per megaparsec, and omega matter of 0.275 plus or minus 1.5%. I'm going to have to move a little faster here to get to the SDSS-II part. So coming soon, this was the first data set from SDSS-II, and now we're really working hard on SDSS-III, and I'll tell you more about that in a minute, but that's a factor of 7 increase over SDSS-II. So we're expecting to have the first BAO results out from SDSS-III in the next couple months. There's a project called HETDEX, which is starting up soon, that will be actually surveying the universe at redshifts above 2. And then there's lots of ideas for how to move forward on this to much larger volumes, ideas for the end of the decade. The Euclid mission, I'm sure you're familiar with. This will survey galaxies at higher redshifts, about 50 million of them. And there's lots of ideas for ground-based concepts, one of which is being talked about for the GTC. And there's also ideas of doing this in the radio. So we've really only scratched the surface of what we can do with large-scale structure. There's really a tremendous amount more that we can learn about the universe from large-scale structure. And there's lots of ideas for how to build these large new projects. So let me focus here in the remaining time on SDSS-III. So SDSS-III is the next phase of the Sloan Digital Sky Survey project. It started operating in summer 2008 and will run until summer 2014. There are 4 surveys on 3 major themes. The one that's relevant to the material I've talked about so far is the Baryon Oscillation Spectroscopic Survey, BOSS, which will be the largest survey yet for large-scale structure. There are 2 projects that are aimed at studying the Milky Way. Carlos knows all about them. And this is called Segway 2 and Apogee. So Segway 2 is using optical spectroscopy of stars to study the outer portions of the Milky Way. And Apogee is using infrared spectroscopy of stars to try to study the enrichment and dynamics of the whole Milky Way, but in particular to get through the dust-enshrouded regions into the inner galaxy. And then finally, we have the Marvels project, which is using the large field of view of the Sloan telescope to do a radial velocity search for planets. These projects all involve new instrumentation at some level, but they reused a tremendous amount of the existing facility. So we're reusing the telescope software, a lot of the sort of know-how for how to do these large public data releases. And the project has been supported from the Sloan Foundation, Department of Energy, NSF, and now over 50 member institutions. So there's really a worldwide effort to try to make this project happen. So just to run through this quickly, the Baryon Oscillation Spectroscopic Survey aims to be the definitive study of the low redshift acoustic oscillations. So this will be 10,000 square degrees of spectroscopy, about a quarter of the sky, involving 1.5 million of these luminous red galaxies out to redshift of order 0.8. And as I said before, it's a 7-fold improvement of the survey. So we expect to be able to get to cosmological distance measurements about 1% or slightly better. And really the first time that we've been able to get through the 1% barrier. There's a simultaneous project to try to discover the acoustic oscillations in the Lyman alpha forest. And the idea here is that any given line of sight from a quasar is actually, as it moves through the intergalactic medium, the neutral hydrogen is scattering particular wavelengths, the Lyman alpha 1216 line, out of the spectrum. And so the resulting spectrum you get is actually a map of the intergalactic medium along the line of sight. Well, for any one line of sight, you would get some measurement of the density, but if you now take a three-dimensional a grid of these quasars, in our case 160,000 of them, then you can actually start to build up a three-dimensional map of the intergalactic medium, and you can look for the clustering of the high redshift matter in that, and you should see acoustic oscillations in that data set as well. And so the goal here is to really use this method for the first time to measure the acoustic oscillation signature at redshift of order 2.5, which would be the first time that we've measured a high precision distance at high redshift. So BOSS is ongoing, and I'll just note that we now have 50% of the data in hand, over 800,000 spectra. And so if you've been, everybody here at the IAC has data rights in this project, and if you have been waiting for the data to be accumulated and to get good enough to use, it is now good enough to use. You should start diving into it, because there's really a tremendous amount of data available. The MARVELS project is using the large field of view to look for radial velocity planets. This does not get to the kind of precision that you can get with a single object of shell spectrum, but it does get you to enough precision to study large numbers of stars down to the precision of needed to find Jupiters. The Segway 2 project has now finished, and it, in terms of data collection, there was 118,000 optical spectra that were targeted mostly in the thick disk and halo. And the idea here is to look for the long-lived kinematic signatures of mergers in the galaxy, and also to look for enrichment signatures from the early phase of the galaxy, hopefully with the earliest supernovae. This is then moving on into the project called Apogee, which is a project to study the entire Milky Way, and in particular to look through the dust-enshrouded region. So to do this, you need to work in the infrared, and Apogee has built a new high-resolution infrared H-band spectrograph. This is 300 fibers and resolution above 20,000, and the goal is to really be able to dissect the spectra of stars to measure the individual elements. Carlos is taking the lead on the abundance measurement side of this. And this was really a unique instrument, the first time that we've been able to do these large sorts of surveys in the infrared. So the goal is to measure 100,000 stars all over the galaxy and really be able to dissect their dynamics and their individual chemical abundances. Again, this project's underway. It's been a tremendous year of activity in Apogee. We've delivered the instrument, gotten it commissioned, started the survey, and collected the first several tens of thousands of stars. I don't track the number day by day, but it's been a wonderful story the past year that things are now moving along. SDSS has had its first data release. DR8 was released in the January 2010 AAS meeting. This included all of the imaging that we've taken for BOSS and SDSS-II, as well as all the Segway and Segway 2 spectroscopy. Just very nice pictures that came out of this for really studying this is the northern galactic cap, removing all the stars and just looking at the distribution of the galaxies. Here's the south galactic cap. So in total, the SDSS imaging covered about a third of the sky, including 10,000 square degrees at high latitude to support subsequent spectroscopic surveys. And for those counting at home, this is actually added up to 1 trillion multicolor pixels. So data sets in astronomy are getting really large. There's wonderful ways to get at the data. So if you're looking to get involved in the project, there's really very powerful ways of getting and querying the data without downloading it all onto your disk. So if you're interested in learning about SDSS-III, there is the project webpage, www.sdss3.org. There's an overview paper and the first data release paper. But a very nice way of keeping up on recent activity is this blog. So if you go to sdss3.wordpress.com or just go to the top page and click on it, you can get the latest updates on what's going on in the project. The collaboration is large. We've now have 51 members, including a very important one here. So, okay. So I'll just close here by saying that we've really only gotten started in large-scale structure. It's easy to imagine that with all the activity in SDSS-I and SDSS-II that we've somehow finished up the topic of large-scale structure, but in reality, we've only surveyed about 1/1000th of the volume of the universe out to redshift of 5, 1/10,000th of the modes that are relevant to the acoustic oscillation, and actually fewer than 1/1,000,000th of the modes that are relevant to the linear regime. So there's an enormous amount of information that's left in the universe for us to uncover and to learn about the earliest phases of the universe through. David Weinberg led a group of us in writing a review article, so let me just advertise that if you're interested in sort of all the various methods for studying dark energy from an observational point of view, this review article, we wrote down everything we know. So this was about 200 pages and plus 50 pages of references. There's really a lot of things here. So if you're a student and looking to get involved in cosmology, this would be a good reference manual here. So to conclude, acoustic oscillations are providing a robust way to measure cosmological distances. You can measure the Hubble parameter and the angular diameter distance as a function of redshift. It's a very clean signature with good reasons for being robust. You can probe the high redshift. You can probe the Hubble parameter directly, and it has adequate precision. We've used it in SDSS to measure the cosmic distance scale to redshift 0.35 to about 2%. We find excellent consistency with the flat universe and a cosmological constant, and we find a Hubble constant of 70 plus or minus 2 kilometers per second per megaparsec, and omega matter down to about 1.5%. But this is really just the start, and large surveys such as BOSS and future projects are going to be pushing this cosmic distance scale to 1% and below over the next decade. So thanks very much for your time.
I think we have time for a few questions. BOSS is focused on this particular redshift 0.35. Why it couldn't be done at lower redshift? I mean, in Sloan you have plenty of galaxies which lower redshift.
Yeah, so you really need cosmological volume. So there's always a competition in a survey between sample variance and the shot noise in the survey. And in the main sample of Sloan, there are a lot of galaxies, but it's actually kind of overkill. You've actually measured the volume, but you spent way too much resource trying to measure it really, really, really well, and you didn't need to actually measure it that well. The result is that you actually have not enough volume to measure the acoustic oscillation well. Now, you can measure it in SDSS in the lower redshift sample, and the 60F survey has done a nice job of measuring it in an even lower redshift sample. But to get to you're really volume limited. You're limited by the amount of volume you have, and you need to get out to larger redshift to get enough volume. I don't think that's on, but yeah.
Okay. In the large scale structure, there are more remarkable features like, for example, the cluster of galaxies or the cosmic voids. So, are you aware of people taking a look, for example, to the typical distance between the cluster of galaxies or the position of the center of the voids as a ruler? So it would be also related somehow to what you're talking about.
Right. So there is work. There is a group that's looked for acoustic oscillations in the clustering of clusters. I think Hootsie was the first author, although I might be misremembering, but I think that was he was first author. And so they do find a signature there. I don't think anybody's looked for it in the clustering of voids. the reason that I don't focus on that is that usually to get to the point where you found accurate positions of clusters or positions of voids, you had to take a lot of spectroscopy anyways. And so when you work through the numbers, it actually becomes more favorable just to do it on the galaxies rather than trying to use the galaxies to then find this other structure. Another way of saying that is even in clusters, you can go out and do a nice cluster survey from imaging or X-rays or whatever you like. But at the end of the day, you still need to make a three-dimensional map, not two-dimensional. And so by the time you've gone to get spectra of all those clusters, you've had to do a project that's as ambitious as SDSS was to begin with. So it turns out not to win fast enough.
Last question.
Please, could you tell us a bit more about this, the use of the Lyman alpha clouds in your scenario? I don't see very clearly how do they fix which is the velocity pattern you are looking for in these clouds to match your 150 megaparsec scheme.
Right. Okay. So the idea there is that we're using the Lyman alpha forest to map the density along the line of sight, and if you now consider many lines of sight, you can cross-correlate positions along the line of sight that are 100 megaparsecs or 150 or 200 megaparsecs separated. And you can look for the correlation in the signature, cross-correlation between two different lines of sight. So in that way, you're really building up a three-dimensional model of the Lyman alpha forest. And normally when you think about the Lyman alpha forest, you're thinking about small-scale structure, maybe they're clouds, however you like to think about it, but normally you're thinking about small-scale structure. That structure is all on far, far smaller scales than 150 megaparsecs, and effectively that's just a noise source for us. But on average, in regions that are big fat regions, 10, 20 megaparsecs across, there will be more absorption than in a region that's a 10 or 20 megaparsec void. And so you're looking for that subtle extra correlation on large scales. Yes, that's correct. So when you talk about modeling it, now you're doing Lyman alpha forest. So yes, we've been doing, I haven't personally involved with that work, but there's a group within SDSS-III that's working on large-scale modeling of Lyman alpha forest. And yeah, they have, you have to